Welcome you all. This is the next problem, which is based on steady flow energy equation. I'm just dictating the problem. The air at a flow rate of 1 kg per second enters the nozzle of jet engine at temperature of 800 Kelvin, 200 kilopascal and velocity of 50 meter per second. It leaves the nozzle at a temperature of 650 Kelvin, the pressure 1000 kilopascal. The heat lost at constant rate of 25 kilowatt from the nozzle to the surrounding. Assume air behaves as an ideal gas. Cp is 1.005 kJ per kg Kelvin. Find the exit velocity of air, neglect the change in potential energy. This is basically the problem which is based on nozzle. First of all, just try to understand the problem. There is a jet engine. A jet engine consists of nozzle. In nozzle, the air enters at the flow rate of 1 kg per second at an initial temperature of 800 Kelvin, 200 kilopascal and velocity of 50 meter per second. That means at an entry of this nozzle, this temperature is 800 Kelvin, the pressure is 200 kilopascal and velocity of air is 50 meter per second. Okay. It leaves the nozzle at a temperature of 650 Kelvin, pressure 100 kilopascal. That means after expansion in nozzle, it leaves at a temperature of 650 Kelvin and a pressure of 1000 kilopascal. Right? So this is the condition of at an exit of this nozzle. That means air leaves the nozzle in this condition. Okay? This temperature is 650 Kelvin and pressure is 100 kilopascal. The heat lost at constant rate of 25 kilowatt from the nozzle to surrounding. That means from nozzle, 25 kilowatt of heat is lost to the surrounding. That means nozzle is not insulated. Be careful. Nozzle is not insulated. There is heat transfer between system and surrounding. What is my system? System is our nozzle and surrounding is atmosphere. That means this nozzle rejects constant rate of 25 kilowatt to the surrounding. Assume air behaves an ideal gas and we know this value of Cp is this one. Then we have to find the exit velocity of air. We have to find exit velocity of air at the from the nozzle, where we have to neglect the change in potential energy. So this is all about the question, because we know that we have already explained the nozzle. Nozzle is a device in which velocity is increased several times at an expense of pressure. This is my definition of. Just we have explained this term in the derivation of steady flow energy equation. Okay, right? So welcome back. Just I'm solving this numerical. Suppose that this data basically air enters into let us suppose this is nozzle. Air enters into nozzle. This is the entry point. This is the exit point. This is nozzle, right? This is nozzle. The air at a flow rate of 1 kg per second enters the nozzle of jet engine. This nozzle used in jet engine. This air enters, that means, let us suppose in this data, this question, mass flow rate of air, this is given, the mass flow rate of air, this is given 1 kg per second. This at entry enters the nozzle of jet engine at a temperature of, at an entry, this temperature is 800 Kelvin. The pressure kilopascal, and the velocity of air at entry, this is 50 meter per second. It leaves the nozzle at a temperature of 650 Kelvin. It leaves the nozzle at a temperature, this is the temperature of air at an exit, this is 650 Kelvin. In pressure, 100 kilopascal. 100 kilopascal. Right. And heat lost at constant rate of 25 kilowatt. This nozzle is rejecting heat. This rejecting heat 25 kilowatt. Okay. This nozzle is rejecting heat at the rate of 25 kilowatt from nozzle to surrounding. This heat is rejected to surrounding. Okay. This quantity of heat, this is 25 kilowatt. Assume air behaves as ideal gas and the Cp of air per kg Kelvin. One more assumption is there is no change in potential energy. Del P is 0. Okay, these are the assumptions. These are the given data, and we have to assume there is no change in potential energy. Right? So, what we have to find? We have to find velocity of air at exit of nozzle. This implies you have to find velocity. You have to find the velocity of air at an exit of nozzle. This is our question. Right? So, first of all, we have observe carefully, and we have to pick one equation because we have derived three different steady flow energy equation. So, pick one. We have to pick one equation. There are three equations. So if you look at very carefully, this amount of heat rejected from nozzle to surrounding is 25 kilowatt. So unit of this heat rejection is in kilowatt, and this mass flow rate is also given. Okay. So better to write this equation in steady flow energy equation in kilowatt form. Okay. So write as per steady flow energy equation. Units are in kilowatt. If you write this equation we have is mass flow rate. This is mass m dot. Mass flow rate. This is h1 plus half n square gz1 plus this q dot is equal to m dot h2 plus v2 square gz2 plus w dot. This is our equation. Well, this is h2. This is h2. This is our steady flow energy equation when unit are in kilowatt. M dot h1 plus half v1 square plus gz1 bracket close plus q dot is equal to m dot in bracket s2 plus half v2 square plus gz2 in bracket close plus w dot. Right? This is our steady flow energy equation when units are in kilowatt. Now, there are some assumptions are given. There is no change in potential energy since del P is 0. This is given. In nozzle, we don't get any work output, and this q dot, this heat is rejected. Q is equal to minus 25 kilowatt, because heat is rejected, therefore the sign will be minus. Okay, so if we are putting this assumption, by carrying out these assumptions, the equation reduces to m dot, say h1 plus v1 square minus q dot is equal to m dot h2 plus v2 square. Okay, this term will be cancelled out, this will be cancelled out, this will be minus q because heat is rejected and we don't get any types of work output, therefore this work will be 0. Right? So this is our, let us suppose this equation number 2. Equation number 2. We know this enthalpy H is equal to CPT. We have to put this value in this equation. So if we put this one, m dot CPT1 plus half v1 square minus q is equal to, this is CPT2 half v2 square. Now we have to put this value. Whatever value we have, we have to put this value in this equation. This m dot. M dot is 1 kg per second. Look at carefully. The CP 1.005 kilojoule per kg Kelvin into T1 800 Kelvin, bracket close, plus half v1 square. Velocity is 50 kg. Just remember one thing. Be careful. We have to write this unit in kilojoule per kg because we know the kinetic energy half, this is written half v square. This unit is in joule. Okay, I have to convert this unit in kilojoule. We have to convert its unit in kilojoule. That's why this will be written. This we have to divide by 1000 MVA square. Now this unit will be in kilojoule. But we have to write this equation in kilojoule per kg because in this every term is kilojoule per kg, right? This can will be cancelled out. The unit is kilojoule per kg. So we have to divide by this term. Don't forget to divide this term by 1000 because unit of this quantity is joule per kg, half v1 square, because mass is taken out. A specific kinetic energy. The unit of this one is joule per kg, but we have to convert into kilojoule per kg. That's why we are dividing by 10 to the power 3. Minus q 25 kilowatt. This is equal to, once again, 25 kilowatt. This is equal to 1 kg per second. Cp 1.005 into T2 is 650 Kelvin plus half into 10 power 3 because we have to divide this one, we have to convert it to V2 square. We have to convert this term into kilojoule per kg. That's why we can just after putting this value in this equation, we will get the value of V2. So V2 is equal to 503 meter per second. If you solve this value, you will get velocity of air at exit of this nozzle is 503 meter per second. So remember, just be careful whenever you are writing this kinetic energy. You have because this quantity, this unit of this quantity is joule per kg. We have to convert it into kilojoule per kg. That's why we are dividing by 10 to the power 3. Same thing is applied for potential energy also, because this GZ1, this unit is in joule per kg. whenever this term will be considered in further numerical, don't forget to divide to this term by 1000 so that it could be converted in kilojoule per kg, right? Because we have only 3 equations. This one equation, that's this unit of this whole quantity is kilojoule, next unit is kilojoule per kg, and third unit is kilowatt. Everywhere kilo is there. Okay, so this quantity we have to divide by 1000 in final whenever you put this value. This is not necessary to see this term by dividing 1000 again and again. So whenever you solve this problem, when you put this numerical values in this equation, just don't forget to divide this term by 1000. So this is the velocity of air at an exit of nozzle. This velocity we wrote this 503 meter per second. Now recall this definition of nozzle. What we have explained earlier, what is nozzle? Nozzle is a device in which velocity is increased several times at an expense of pressure. Look, it is a device in which velocity increases several times. That means velocity of air at inlet is 50 meter per second and velocity of air at outlet is 503 meter per second. That means velocity increased 10 times at an expense of pressure. That means pressure should decrease. So look at this, pressure at entry is 200 kilopascal, right? And pressure at exit is 100 kilopascal. That means pressure is decreasing at the cost of this decrease in pressure, at the expense of pressure. Pressure at inlet is 200 kilopascal and outlet is 100 kilopascal. That means 100 kilopascal pressure is decreased at an expense of pressure. This velocity is increased 10 times, 500 meter per second. So this is the very beautiful problem. This in this numerical we have solved, and go through this one. I hope everything is very interesting and you will understand very good. Okay, thank you very much. We'll meet in next session.